Afternoon, my name is Wesley. I'll be presenting my project on multi-wavelength Raman Spectroscopy of crystalline and nano-sized carbon materials. The project was supervised by Dr. Rudolf Erasmus. A brief outline of the presentation will include some theoretical background on Raman spectroscopy, as well as a look at diamond, graphite and carbon nanotube structure, some experimental method, and a look at some analysis of the different wavelengths of lasers and single carbon nanotube dependency on temperature. So what is Raman scattering? So in general, we understand that phonons scatter off molecules elastically. This is known as Raman scattering. But a certain amount of these photons, about 1 in 10 million, scatter inelastically. This is known as Raman scattering. In Raman spectroscopy, we use high-intensity radiation in the visible wavelength and infrared wavelengths and pass it through to a sample. These phonons then excite the sample to a virtual state and harmonically polarize the samples. This polarization can couple with other excitation states within the molecule, most likely vibrational, electronic, or electronic states. If a molecule polarization does not couple with any of these other excitation states, we tend to see Rayleigh scattering. This means that the incoming photon has the same energy as the scattered photon. But if this polarization does couple one of these vibrational nodes, we tend to find that there is Stokes scattering. So there are two types of Stokes scattering that we look at. The primary one, known as Stokes scattering, is when the photon tends to have more energy than the molecule that's being excited. Hence, the molecules tends to absorb some of the photon's energy. The molecules drop down to energy state above its initial state, and the photon is scattered with a lower energy. We also have anti-Stokes scattering, which is where the actual molecule is at higher state energy, hence the photon is now absorbing energy and is released at a high energy level. So we also understand that in molecules, atoms are in constant motion. This means the molecule always feel transitional and rotational motion. But these vibrational modes are highly dependent on the type of atoms as well as the type of bond structure within the atoms, in the molecules. So these different vibrational modes can either be Raman active, but this requires that these vibrational modes actually change the polarization state. Also, there are certain vibrational modes that do not change the polarization, hence they are not Raman active. Hence, Raman spectroscopy cannot pick up all vibrational modes within the system. Here we have an example of perfect Raman shifts. We have diamond, silicon, and germanium, just showing the bonding shifts picked up by Raman's spectroscopy. Cool, so the samples that we'll be looking at in our experiment is the face-center cubic structure of diamond. It's sp3 hybridized, meaning that all the valency electrons are involved in bonding. That's why there's no conduction involved. We'll also be looking at allotrope of diamond, or known as graphite. It has a planar structure with a honeycomb lattice build-up. It's sp2 hybridized, hence there are additional valence electrons, hence graphite is conductive. We'll also be looking at interesting single-wall carbon nanotubes, which are synthesized by the use of a single layer of these planar structures in graphite known as graphene and formed into these interesting physical tubes. So, short experimental method. Here we have on the left image the laser and its peripheral optics being focused in the right on the microscope. The microscope then focuses the laser onto a sample. The reflected light is then again processed through another set of optics, which filter out the highly intense Rayleigh scattering from the less intense Raman scattering. The Raman scattering is then processed by the computer we see on the right into the Raman spectrums. For the second part of the experiment, we actually had to use a furnace to incrementally increase the temperature of the single-wall carbon nanotubes. So this is the first spectrum, characteristic spectrum, Raman spectrum of diamond. We have a primary peak at 1,332 with a full width half maximum of 1.2, indicating the interaction of two cubic sublattices and the purity of the diamond crystal. This also implies that Raman spectroscopy can be used to identify between diamond and zircon crystals. Over here we see that the red laser on the right produces a more intense spectrum than the green laser on the left. Here we have the graphite Raman spectrum. The sp2 hybridized stretching of the carbon bonds gives rise to the G band seen here at about 1600. The G band is a characteristic phonon mode in the planar system of graphite. It also indicates the presence of sp2 hybridized carbon atom bonding. We also have the disorder-induced band, known as the D band. It's a special phonon mode referring to the disorder within the system. In graphite, this D band is looking at the actual sp2 hybridized edges of the graphite sheets. Again, we see the red and green laser. In this case, the green laser produces stronger peaks, and the red laser produces less intense peaks. Now we get to single-wall carbon nanotubes. Again, we see the G and D bands present, and interestingly, they can be used in a ratio to determine the quality of the single-wall carbon nanotubes. Since the G band is continuous throughout the surface of the single-wall carbon nanotubes, and the D band is localized to where there are defects in the system. But now we also pick up some new peaks known as the radial breathing modes. These are characteristic phonon modes in single-wall carbon nanotubes that relate to the carbon vibrational states in a radial direction. They're also inversely proportional, the peak's amplitude, to the radius of the single-wall carbon nanotubes. Again, we see the green lasers producing more intense peaks than the red laser. So in the second part of the experiment, we looked at heat dependency on the single-wall carbon nanotubes. On this diagram, we can see a consistent downshifting of all main peaks, the G, D, and radial breathing modes, as temperature increases. The main peak at around 1200 is due to the mercury lamp above. This is just to prove that the downshifting is due to temperature change and not the calibration shift. We now look at a zoomed-in image of the D band. We see as temperature increases, the full Witts-Hart maximums start to increase. This indicates the presence of an increasing amount of free electrons within the system, proving that the single-wall carbon nanotubes are becoming more conductive as temperature increases. We also see that there are different peaks forming within the initial G band. This is indicative of the optical energies being relative to the temperature within the system. Hence, the different single-wall carbon nanotubes will be moving in and out of resonance as temperature increases. Here we look into the rate of breathing modes of the system. They don't downshift as much as the G and D bands, and also don't change the shape as much. But the change that does occur is related to the softening of the carbon covalent bonds due to the increase in thermal temperatures. The next two graphs indicate the relation between Raman shift and temperature. The right, we have the rate of breathing mode graph, which has a gradient of about negative 0.01. On the left, we have the G bands, gradients of about negative 0.03. This indicates the rate of breathing modes are less affected by thermal heating than the G bands. So now we get to an interesting phenomenon in our experiment. So as we were heating the sample up from 700 degrees Celsius to about 800 degrees Celsius, we noticed that we lose the characteristic G band that states that there are carbon bonding within the system. It's totally lost in the 800 degrees Celsius graph. This might be due to oxygen leak within the system, so the carbon tends to be burnt off in that situation. But then we move forward and look at the cooling of the system. So again, we see on the right of the reference peak, there's no carbon bonding. There's no carbon within the system according to the Raman spectrum. But we do start to see new peaks forming, indicating new bond formation within the system. So this disproves that oxygen actually moved into the system and burnt off the sample. So we decided to have a look at the sample under a microscope, and this is what we noticed. So due to heating, some flakes did flake off the main sample due to thermal expansion, but the flakes were extremely spread out. But as the temperature cooled down, they started to conglomerate in these little systems here. Also, we noticed this was the original sample. But we noticed the precipitation of these perfect tubes, which is strange because if according to the Raman spectrum, there's no carbon left in the system. So we aren't too sure what these tubes are actually made of and what's happened to the sample itself, since the carbon has, theoretically, according to the experimental spectrums, been removed totally from the system. Unfortunately, the time constraints with the project prevented another analysis, another experiment to relook at this situation. So in conclusion, The green laser would be highly recommended in Raman spectroscopy, especially with graphite and single-wall carbon nanotubes, as they produce stronger peaks within the spectrum. We also found that Raman shift is dependent on temperature. The rate of breathing modes are less affected by temperature increase than the G and D bands are. The observed single-wall carbon nanotubes are not fit for use under high temperature conditions, and differently synthesized group of single-wall carbon nanotubes will have to be used in high temperature situations. Thank you.